Okay, let's watch what's happening here. Related rates. We'll use this first problem as an introductory to what we are doing. Think of how difficult this problem is if you were to ask it of somebody. They would have no idea how to figure it out. The area of a circle increases at a rate of 20 inches squared per minute. At what rate is the radius increasing when the radius of the circle is at 5 inches? So, I know. It just, you read it and you're like, okay, I've got no idea. Well, I agree. We've got no idea. So here's what I like to do. Yeah, right, exactly. Yeah, answer's 1. No. So we got to wrap our brains around this and try to muddle through it. The area of a circle increases. So I'm going to start just like I did last year, where, what do you think we put in this box? A picture. Yep, we're going to put a picture. Sure. Yep, exactly. Yes. Visualize. Formula. Function. Graph. Only we're not doing those this time, so no, we're almost there. We first visualize the problem, and what we have is we have a circle that it's getting bigger. Okay, who knows why? But this circle is becoming larger. What's that? A balloon. No, a balloon is 3-dimensional, so that would be like example 2, volume of a ball. So we'll do a balloon problem later. Okay. Shh. Now, here's the important part, okay? The area of the circle is increasing at a rate. Rate. What is another word for rate? Derivative. Yeah, derivative. So, I'm going to write down some formulas over here and some given pieces, but you know that the derivative, so A prime, the derivative of the area is equal to 20. The question is, at what rate is the radius increasing? So at what rate is the radius? What is an expression for rate of the radius? R prime. R prime is what we're trying to find. We don't know that one. Okay? When the radius is 5 inches. So we don't know what R prime is, but we do know that R is 5. So you can see here we've got some knowns, we've got some unknowns. We're trying to solve for R prime. Okay? And the other thing that we know that's probably helpful is we have a formula for area of a circle. What is area of a circle? Pi times R squared. What you think? What do you think? You like that? Okay. So, here's the tricky part, and here's why we call it related rates. Can you give me a variable that's changing in this problem? R is changing. What else is changing? A is changing. Would you also agree the circumference is changing? The diameter is changing. But do you know what they are all changing with respect to? You see, what? What'd you say? No, that's totally incorrect. All right. This is what you got to think through your brains. This is the conceptual piece right here. Normally when we take a derivative, we say dy over dx. That's the rate of change of y with respect to x. What are we taking the derivative with respect to? What else is changing here? Hint, you can't see it. Something here. Time! Time! So I said it? Solveig said time. Very good, very good. So A+ for Solveig and for Tyler. So nice job. All right, time is changing. Would you guys agree that as time goes on, the area gets bigger? Would you agree that as time goes on, the radius gets bigger? Yeah, so time is the variable that we're taking it with respect to. Do you see a t, a variable time, pop up there at all? So therefore, we have to use implicit differentiation. Notice if we had dy over dx of the expression x squared plus 3x plus 1, well, that's easy, 2x plus 3, but that's because you're taking with respect to x, and the function is expressed with x. But when you don't have an x, and you have y's in there and z's, you have to use that implicit differentiation piece, right? So that's what we have to do. So we are going to take the derivative. So this box is derivative. So this one's formulas, this one's derivative. And I'm going to take the derivative with respect to what variable? Time. Of my area function. I'm going to take the derivative with respect to time of a equals pi r squared. Anybody want to guess what the derivative of a is? A prime. We'll plug in the 20 in a second. A prime. Anybody want to guess what the derivative of pi r squared is? 2 pi r, r prime. Anytime, because the derivative of a is 1, and we attach an a prime. The derivative of pi r squared is 2 pi r, and we attach an r prime. Anytime, because t does not pop up here, the only way we would attach something is if we had a variable with t. And we don't have that. So now, our last box is we solve. And what is a prime? A prime equals 2 pi r, r prime. So a prime, I put 20 in there, equals 2 pi. What's r? 5. What's r prime? We don't know. So we just solved now. So we got 20 is equal to 2 pi 5 r prime. Divide both sides by 10 pi, and you get 2 over pi equals r prime. Or you could write it like this: 2 over pi, and what is, we need the unit here. We're talking about the radius, so it's going to be inches per minute. The area is inches squared per minute. The radius is just going to be one dimensional, so it's just going to be inches per minute. If you want to leave it as 2 over pi, or if you want to leave it as 0.6 inches per minute, either way is fine. I'll accept either. Okay. So do you see what's happening here? The most important part is that you set up the visual, and then you take the derivative. Okay. So once we get the visual and the formula, taking the derivative, we can solve it from there. But for most people, the problem is getting from box 2 to box 3. That's where they really struggle. It's like, well, what's the correct formula? What do I really need to know? What's changing here? And you guys, I showed you one problem. You know how it is with word problems. There's hundreds of different types. And so I've really tried to give you good problems in the book, but also problems that we are going to do in class. So, is this? If you saw another problem like that, could you do it? Okay. So following that example, watching the video is going to be crucial. We're going to do one more today, and you won't have an assignment, but tomorrow you will, and you're going to have some time in class to work on it. Okay? The volume of a ball is increasing at a rate of 10 cubic centimeters per second. What rate is the diameter increasing when the volume is 100 cubic centimeters? Not per second, but just volume is 100 cubic centimeters, okay? I'm not very good at drawing a sphere, but I'm going to try. There's my best job as a sphere. And it's increasing at a rate of 10 cubic centimeters per second. So tell me something to write down. Not A, but V prime. V prime is equal to 10. Very good. So the derivative of the volume is equal to 10. We know that. What else do we know? Oh, very good. Volume formula is going to be 4/3 pi r to the third. Memorize them? No, I'll give you the formulas. Okay. We know that the volume is equal to what? 100. And what are we trying to find? Not just the diameter, but diameter prime, d prime. Very good. Equals question mark. Very good point. Larry sees it right away. We do need to know the original D, or the D at this spot, but I'm going to allow the problem to develop so we can see why, because most people wouldn't see that right now. Okay? So first of all, I'm going to make a suggestion right now. Does everybody understand that right now we have a conundrum here, because we've got a formula with an R, but we know nothing about R. Rather, we want to find D. And what a lot of people do is be like, well, diameter is double, so we'll just double it in the end. Well, not necessarily. It doesn't always work like that. So, any thoughts? Can I substitute something here? Well, see, the problem is if I take the derivative of that right now, v prime equals, if I multiply by 3, I get 4 pi r squared r prime, right? We don't know the current radius, and it would give us, we would end up solving for the rate of change of the radius. But I want the rate of change of the diameter. So I got to change this radius to diameter. So I have a substitution here. Radius is equal to 1/2 d. Well, now I've got a formula I can use, right? I got volume is equal to 4/3 pi times 1/2 diameter to the third. What is 1/2 to the third? 1/8. And then 1/8 times 4/3. 4/24. What's 4/24? 1/6. So really, what you have is, we're going to use some of this box here. Volume is equal to 1/6 pi d to the third. So volume can be written in two ways. You can either write it with a radius, or you can write it with a diameter. Okay? And we know that the volume is equal to now 1/6 pi d to the third. Now, when we solve for it, we're going to get a d prime, correct? So let's take the derivative with respect to what? What's kind of the underlying thing here that's changing? Time. They're all changing with respect to time, which is what makes these problems tick. Tick time. Yeah. Okay. Okay. So what's the derivative of v? When I take the derivative of that, I get v prime. 3 times 1/6. 1/2 pi d squared d prime. Very good. Yes, so this is my derivative. I will now, Megan, I will now do my substitution stuff, okay? So v prime equals 1/2 pi d squared d prime. Now we're going to do what you said, okay? We're going to put in that 10 for the v prime. So I've got 10 equals 1/2 pi times that d squared times d prime. Now, did everybody catch what Larry said originally? He said we need to know the original diameter, or we need to know the diameter at that time. We need to know the diameter when the volume is 100 cubic centimeters. What is the diameter at that point? Because I've got to substitute that in here, don't I? Yeah, you just solve for it. I know V prime is 10. I don't know the D prime, but that's fine. That's what we're trying to solve for. I need to know the current diameter. How could I solve for the current diameter? I know the current volume is equal to 100. Whoop. 4/3 equals 1/6 pi d to the third. Is that our formula for diameter? That will give us the current diameter. Multiply both sides by 600 equals pi d to the third. Divide by pi. Somebody got their calculator? And then let's take the cubed root of that and raise it to the 0.33 power. 5.76. So I solve for the current diameter. I'm going to take that and I'm going to plug it in right here. So 10 is equal to 1/2 pi times 5.76 squared d prime. Or 10 is equal to, let's multiply that out, 0.5 times pi times 5.76 squared. You guys got 52.12? Divide both sides by 52.12. .19. So the rate of change of the diameter is 0.19. What is the units? 0.19 centimeters per second. We'll pick up with that later. What did I do, the 1/2 pi? I took 1/2 times pi times 5.76 squared, and I got the 52.12. So it all comes out to 52.12. We'll try again tomorrow, okay?